Okay, this question is number 5 in topic assignment 2.2.4. It asks us to find the volume of a solid generated by revolving the region bounded by three curves around the line x equals 8. And the three curves are y equals negative x squared plus 8, y equals 0, and x equals 0. Those are the x and y axes. And we're revolving around the line y equals 8. So I'm going to start with a sketch. Let me draw in some axes here. And I know that the curve y equals negative x squared plus 8 is an upside down parabola that's been shifted up 8 units. So it's going to go up to y equals 8. And I could figure out what these intercepts are, but I'll wait and see if I need to do that. The line y equals 0 is just where the graph has a height of 0. And the line x equals 0 is the y-axis. And one of the things that having a sketch now tells me is that the region that I'm looking at is not the entire region here. I'm only interested in the region that's bounded by these three curves. So technically, I could either be looking at this region right here, that's bounded by the pink and the green and the blue lines, or I could be looking at this region here, that's also bounded by the pink, the green, and the blue lines. So actually, this question isn't really very well worded. So we're going to have to make an assumption here, and the assumption that I'm going to make is that we're looking at the first of those two sections. To erase some of this that we don't need, and I'm going to erase the pink curve as well, because we're not going to be using that part of the sketch. All right, so now I'm going to draw another sketch. And this one is to help me visualize what the solid will look like. I'm not an art teacher, and there's a really good reason for that. But I'm going to do my best here. I'm going to try to replicate just the region that I'm integrating, or the region that I'm going to rotate. And I have to notice here that I'm rotating around the line x equals 8, which is somewhere over here, right? So I'm going to be rotating it around that line there. So my solid, when I'm done with it, is probably going to look something, let's try that again, something like this. Now this is not to scale, but that doesn't matter. I'm just trying to get a feel for what the thing is going to look like. When I've rotated this around this vertical line here, I'm going to end up with something kind of looks like this. Okay, now I'm going to take a slice of this, all right? If I take some random washer out of the middle of this, then that washer might look something like this. All right. And the other thing I'm going to keep in mind as I go here is that my y-axis is over here. So this is x equals 0, this is x equals 8, and this would be x equals 16 over here. That's not going to matter, but it might help us situate ourselves in the scenario. Okay, so I'm going to call this washer here, and in fact, I'm going to color it in a little bit here. What I'm looking for initially is what is the area of this washer. So this green region that I'm coloring in here now, I'm going to call that A for area. And ultimately, what I'm going to want is to find the sum of all of the areas, as we go. See how the thickness of the washer is a change in the y direction here. The thickness is a change in y. It's a how do I describe it? It's a vertical change, right? So that tells us that we're going to be integrating with respect to y. It also tells us that the limits of integration have to be in terms of y. And since y equals 0 is down here and it goes up to whatever that number is, I'm going to be integrating from 0 up to whatever this number is. And we established in our initial sketch that that was 8 because the equation x squared, y equals x squared, negative x squared plus 8 is an upside down parabola shifted up 8 units. So we know that's 8. So we know that we're integrating from 0 to 8. We know that we're looking for a generic area and that the integrating from 0 to 8 is going to add up all those similar areas, and that we're integrating with respect to y. So that's the sort of basic setup of this problem, and unfortunately that's the easy part. So now what we have to do is try to figure out what is the area of that washer. let's start by noticing that it's a circle with a circle cut out of it, okay? And we know in general by now that to find the volume of a solid rotated around a vertical line or a horizontal line for that matter, we use the washer method, and that the area of that washer, or the area of that washer, essentially, I'm gonna go, let's see, I'll go over here. That area is going to be, because this is a circle, it's gonna be pi r squared minus pi r squared. And I like to use capital R for the outside radius of the outside circle and small r, lowercase r, for the radius of the inside circle. Now let's see if I can draw these in here. It's a little tricky. I'm not giving myself much room here. But this right here in pink is my capital R. So let me go over that in pink, right? When I talk about the outside, the radius of the outside circle, that's what I'm talking about. The radius of the inside circle is, well, that doesn't really work. Let's try it in white. Kind of hard to see that there. But the radius of the inside circle is that white line right there. That's the radius, okay? So that's going to be, I guess I'll leave that in white. So my job now is to figure out what those radii are, right? I can change the form of this expression here. I can write it as pi times big R squared minus little r squared just by factoring out the pi. And that's the form that you're used to seeing it in. There's no change to the formula with these problems. The thing that's different is how we express that radius, because we're not rotating around the line x equals 0, but x equals 8. All right, so let's talk about that large pink radius first of all. How long is the line segment that goes from the y-axis here, x equals 0, out to the line x equals 8? Well, it's 8. So that's not a difficult thing to figure out, all right? So this capital R here is just going to be 8, and ultimately that will be 8 squared. The little r is a little bit harder, but we can still do it. What we're looking at here, you know what I think I'm going to do is I'm going to blow this up. And I'm not going to leave this on the screen at the end because I won't have room. But let me blow this up a little bit. So here's my y-axis. Here's my x-axis. Here's the line y. Sorry, I keep saying that. X equals 8. Here's x equals 0. And I'm looking at something that sort of looks like this. And to find the radius I'm interested in right now, I'm looking for this distance right here. Right? I want the length of that line segment, but I want it for wherever I happen to be between y equals 0 and y equals 8. Right? I'm not looking for it for a specific x value, like this x value here, or this x value here, but for any possible generic x value. Tidy this up a little bit. All right, so what I'm going to do to find that length is I'm going to look at what that length is right there, and then I'm going to subtract off the part I don't need. So I'm looking at 8 again, and I'm going to subtract something off, right? And what is it I'm going to subtract off? Get rid of this stuff here. I'm going to get rid of all of that. What I'm doing is I'm subtracting this much. Oh, I use a different color or something here. Subtracting this much, which is some x value. And my job now is to figure out how to write that x value. And if you'll recognize, this is the critical piece right here. It's the x value that gives us the y value of the function, right? Because we're integrating with respect to y, I need to write x as a function of y, and then no matter which x I pick here, I'll get a y value that goes with it for that line segment minus that part of the line segment. Okay, so how do we do that? Well, all I need to do is take the oh, wrong pen, take the equation that I was given for this curve and write it so that instead of y equals negative x squared plus 8, I have x equals something. And that helps me define what that x value is, where I take off the piece I don't need, piece of that line segment that I don't need. So I'm going to go erase this screen, and I'll just do it here. Erase all of this drawing here, and recognize that what I'm looking for now is a way to write the expression, the equation y equals negative, I'll just write it here, y, wrong pen, y equals negative x squared plus 8 as an x equals expression. So that's just an algebra, I don't know, I want to say like maybe a Math 99 problem where you're solving for x. We're going to subtract 8 from both sides. That gives me y minus 8 equals negative x squared. To get positive x squared, I just negate both sides. I get 8 minus y equals x squared. And then if I take the square root of both sides, I get x equals the square root of 8 minus y. So x equals the square root of 8 minus y is another way to write the equation y equals negative x squared plus 8. In the original version of the equation, if I plug in an x, it'll spit out, the function will spit out a y. If you give me an x, I can give you a y. In this version of the equation, if you give me a y, I can tell you what the x will be that goes with it, right? So that is the expression for, I'm going to go back up to my really small drawing here. Let's see if I can figure out what's a good color to use here. I'll use maybe blue. That's the expression for the x value right here on the x-axis that tells you how much of the pink, how much of the line segment to take away to leave you with the radius of the inside circle, right? So we want to know what the radius of the inside circle, which is in white here, and we want to figure that out, we have to take 8, which is the whole radius represented by the pink line, and subtract away the stuff that was over here that we don't need. That's how we find the radius, little r, right? It's going to be 8 minus some x value. And that x value is going to come from here. Okay, so that's the hard part. I'm now going to do some more erasing because I won't have room otherwise. I'm going to write this new version of my equation. Let's see, I'll just make a note here that this is x, and x equals the square root of 8 minus y. All right, and I can erase that as well. So now I'm going to translate all of this back up into this expression here, this equation for area. All right, I've taken this r and translated it down. We know that that long, the radius of the outside circle, the outside of the washer, that radius is 8. So when I rewrite this one more time, I'm going to get that it's equal to pi times r, capital R squared, well that's just 8 squared, minus little r squared. And little r is all the stuff here in yellow, which was 8 minus x, and x is the square root of 8 minus y. All right, so I've got 8 squared minus this other whole expression squared, and that's going to be times pi. And that's what the area of that washer is. And so that now needs to go in here. So let me rewrite my integral. I have the integral from 0 to 8 of pi times 8 squared minus 8 minus root 8 minus y. Oops, I forgot my minus. 8 minus y all squared dy. And that is how you set this up. Now, there's algebra involved. I'll go ahead and finish this if you don't feel like you need to watch the rest of it. because you know how to do the algebra. That's absolutely fine. But that's how you set these up. And that really is the hard part. Okay? All right, let's see if we can finish this up. I'm going to bring my constant of pi out front. And I'm going to do a little simplifying. That 8 squared is just 64, so that's no big deal. Minus. Now when I square this whole quantity here, I'm going to get 8 minus, let me do this. Recall that a minus b quantity squared is a minus 2 times a times b plus b squared. In this case, a is 8. I'm looking at this 8 right here. So I get 64 minus 2 times a, which is 8, times b, which is all of this 8 minus y. I keep forgetting my minus. Square root of 8 minus y, plus b squared. Well, b is root 8 minus y, and I'm going to square that. Right? That's just from algebra. So now I have 64 minus 64. I'm distributing that negative sign. So I'm going to have 16, but I'm going to have a plus 16, the root of 8 minus y, plus, when you square a square root, you just get the argument. So I've got that. That's simplified. And of course, these go to 0. So now I have pi, the integral from 0 to 8 of 16 root 8 minus y plus 8 minus y dy. I'm going to do that as 3 separate integrals. Actually, let me change this a little bit. Okay, I'm going to do this as pi times 3 separate integrals. One is 16 the root of 8 minus y. Actually, I think I'll just do it as 2 because I can integrate 8 minus y easily enough without splitting it up. Now I'm going down here. I have pi on the outside. I have 16. Now the reason I split these up is because this one is going to require u substitution, but I don't need to apply u substitution to this piece here, right? So if I use u substitution here, I'm going to say let u equal 8 minus y and du equals negative dy. I want a negative dy, but I don't have one, so I'm going to introduce that negative. But I can't just do that, right? If I introduce a negative there, then I also have to balance it out by including a negative, let's just say outside. So, because it's a -1, so I can factor out a -1. I can bring the -1 outside because it's a constant. So I've introduced this negative, but I've also then balanced it by introducing that negative. And the reason I've done that is that I want negative dy, like I have here, because that's what my du is. So there's my du integral. And since 8 minus y is u, I now have the square root of u, or u to the 1/2. And that's going to be a lot easier to integrate. One thing I will have to keep in mind is that it's y that goes from 0 to 8, right? So I have to change my limits of integration. If y is 0, u is 8. And if y is 8, u is 0. So I have new limits of integration. All right, so on top of that, of course, I'm going to have this plus the integral from 0 to 8 of 8 minus y dy. I do not know that I'm going to make this on one screen here. This is equal to pi times the integral. Oh, you know what? I forgot to bring down my -16 here, and that's really important, right? That's from here. It's really important because it's now part of my problem, because I introduced the negative with the dy so that I could integrate, so I could turn that into du. I also have to introduce it in the front, but that means I also have to carry it through the rest of the problem. Now that's okay, because I now have this really nice property that negative the integral from a to b is the same as the positive the integral from b to a. So now I can just change that to the integral. I forgot my 16 as well. Let me fix that. There's my 16, positive the 16, the integral from 0 to 8. Now it kind of looks like we're just back where we started, right? Integrating from 0 to 8, and you might find yourself wondering why we've gone to all this trouble. Well, we don't always get the same numerical bounds. So it is important to make sure we've taken these steps. The numerical bounds will often change when you're plugging values in for y or x to determine what your new bounds in terms of u are, right? So I'm going to integrate u to the 1/2 du. And now notice 0 to 8. I have one integral in terms of u and one in terms of y. That's okay. Close those parentheses. All right, I'm going to take this to another screen so that I can have a little more space. I just don't have enough room here. So I'm going to pause the video just long enough to copy this out onto a new screen. There we go. I can show you where the problem was. When I very carefully noted to you that I was distributing my negative sign here, I did not distribute it to this term right here. That should be a negative. So this should be minus 8 minus y, which is minus 8 if I distribute now, plus y, should be a minus. That's going to be a minus, that's a plus, that's a minus, that's a plus. When I go to the next of the process, getting to about here is really the hard part. And the rest is a little bit of basic calculus and a lot of algebra. Really setting it up is the hardest part, and it's because it's being rotated around a line other than either the x or y axis that it's a little bit tricky. All right, I hope that was helpful.
Let's talk about writing proofs in trigonometry. Proofs are how mathematicians talk to each other. Well, not really, but in a way they are how we share fundamental mathematical ideas that, once established, can be used over and over. After something has been proved, it is unquestionable, and anyone can use the result to do bigger and harder problems without first having to stop to establish each piece. The trigonometric identity sine squared plus cosine squared equals 1 should be familiar to you and serves as a good example of why proofs are important. If I am asked to demonstrate that 1 plus cotangent squared equals cosecant squared, I can start with the known identity sine squared plus cosine squared equals 1, because that one has already been established. Imagine if you had to prove that one first each time you wanted to use it. Something you should know before we start is that when you see someone demonstrate any kind of proof, chances are that they know exactly what each next line is going to look like. They have probably worked out the steps beforehand and are just showing you what those steps are. In reality, writing proofs is much messier than that. In another video, I'll show you what I mean by working through a proof I haven't prepared in advance. There are multiple ways to write proofs. In this video, I'll show you how to prove a trigonometric identity the way I require my students to do it. Your instructor might want you to do it a different way. If no particular method is dictated, then this technique will almost always work. Since this is the first time for most students that they've had to write a proof on their own, I feel it's best to give you one strategy so that you can focus on the logic and the importance of the details. As a student, I always felt like writing proofs was some mysterious skill that you had to figure out on your own. That's because there are so many different ways to do it. This is just one, but it is highly structured and should serve you well in most cases. Let's prove the identity tan theta over secant theta equals sine of theta. This is a very easy proof, but it will demonstrate the process. Then we'll do some harder ones so that you have some other models. Begin by writing out what it is you're going to prove. Tangent of theta over secant of theta equals sine of theta. This is a statement that you are making a claim and that what follows will demonstrate that your claim is true. Some mathematicians and some instructors may have you write required to prove or RTP to the left of this statement. That helps establish that it is a claim rather than an assumption, and that there is more to follow the initial statement. Adding that is not wrong, so I'll leave it. Now we'll select one side of the identity and show that it is equivalent to the other side. This is where a lot of people get lost. Since you are trying to prove that the two sides are equal, the one thing you must never do is say that they are equal. You have to demonstrate that they are equal using logic and algebra. The side that you choose is up to you, but it is usually easier to do the proof if you start with the more complex looking side. That's because there's more on that side to work with. So we'll begin with that. I will choose the left-hand side of this identity and show that it is equivalent to the right-hand side. Since I am using this to communicate with others, even if it is just my instructor, I must be very clear about each thing I write and what role it plays in the process. To that end, you must write LHS, which stands for left-hand side, at the beginning of your proof. Some instructors may not require this step, but I do. Next to LHS, I will state what the left-hand side is, namely tangent of theta over secant of theta. I note that these are equal since it is simply a statement of fact that the left-hand side of my identity, which was given to me to prove, is in fact tangent of theta over secant of theta. The rest is up to me. I have to show that this expression is equal to another expression, which is equal to a third, and so on, until I have found a way to write it so that it looks like the right-hand side. To do that, I'm going to use a series of trigonometric identities that have already been proved, or which I've been told that I can use. For example, algebraically, I can write tangent of theta over secant of theta as tangent of theta times 1 over secant of theta. All I've done is use a little bit of algebra to write this expression as a product instead of a quotient. Now I'll use some trigonometric identities. One is that tangent of theta can be written as sine of theta over cosine of theta. Another is that secant of theta is 1 over cosine. More importantly for me, 1 over secant is cosine. So 1 over secant of theta can be written as cosine of theta. Now we can make the observation that the cosines can be canceled. After that, when I tidy up my work, I just have sine of theta. Well, this is exactly what I was trying to prove, that tangent of theta over secant of theta was equal to the sine of theta. And I've done that now, not by making any assumptions, but by using some previous results and showing algebraically and logically that the expression tangent of theta over secant of theta is equivalent to the expression the sine of theta. There's one last step here. At the beginning, I wrote LHS for left-hand side. At the end, I'm going to write that this is equal to RHS, which stands for right-hand side. So ultimately, what I've shown is that the left-hand side is equal to the right-hand side. And there are several steps in between, but each one is equal to the one before. And that's the sort of thread of logic that we want to use in these. As I said before, there are multiple other ways to write proofs, but trigonometric proofs are easy in a way in that you can always use this strategy to show one side of your identity is equal to, algebraically, some other expression. And then you can just continue playing with those expressions algebraically and using trigonometric identities that you already know to rewrite the expression until it looks the way you need it to look. It sounds simple, and sometimes it is, and sometimes it's more complex. Let's try another one so that you can see what I mean. My instructions might look something like this. Verify the identity cotangent of x times secant of x all over cosecant of x equals 1. The left-hand side looks considerably more complex, so I will start with that side again and show that it is equivalent to the right-hand side by demonstrating several intermediate algebraic steps. We have to remember that we are required to prove, although for some people that step may be optional, we are required to prove that cotangent of x times secant of x all over cosecant of x is equal to 1. And then when we begin, you may also want to write proof to show that you're about to prove this statement. Now let's write left-hand side equals, and we'll rewrite the left-hand side. Cotangent of x times secant of x all over cosecant of x. Notice that I have not done anything in this step to change the left-hand side. I have not done my first algebraic logical step. I have simply rewritten the left-hand side. This is important because you're establishing a starting point. It's really tempting, especially with ones that seem like they're going to be easy, to dive in and start rewriting things. But your first step should always be just to rewrite one side or the other of the identity. Now that I've done that, I can start playing around with it. I'm going to start the way I did the last time, by writing this quotient as the product of the numerator, cotangent of x, times the secant of x, times 1 over the denominator, cosecant of x. I've simply changed the form that this expression takes. Now I can start playing around with each of the three pieces here. The cotangent of x can be written as cosine of x over sine of x. Secant of x can be written as 1 over cosine of x. And 1 over cosecant of x is sine of x. Now I can see that sine of x over sine of x will cancel, and cosine of x over cosine of x will cancel. And everything has canceled now, and the result, therefore, is 1. Well, that's exactly what I wanted. The right-hand side of the identity that I'm trying to prove is 1. So at this point, I can just say that that equals the right-hand side. And I'm done. These two examples were very similar in the strategy used. In the next video, I'll discuss a few other strategies, and we'll do some examples using those.
Okay, so this is where we left off. We have pi times 16 times the integral of u to the 1/2 from 0 to 8, plus the integral of 8 minus y from 0 to 8. Okay, and there are two different variables there, but that's okay. We changed the variable in the first integral because we needed to do a u substitution. All right, so carrying on here, this is going to give me pi times 16, integrating u to the 1/2 gives me u to the 3/2, but I'll divide by 3/2, which is the equivalent of multiplying by 2/3. And I need to evaluate that from 0 to 8. And then I'm going to add to that the integral of 0 to 8, the integral of 8 minus y. The integral of 8 is 8y. the integral of y is y squared over 2. That will be evaluated between 0 and 8. And all of that's going to be times pi. I'm just leaving the pi on the outside. So I have 32 thirds here. 16 times 2 is 32 divided by 3. And I'm going to have u to the 3 halves u to the 3 halves evaluated at 8 is 8 to the 3 halves. And at 0 is 0 to the 3 halves. And that's this first one. That first integral has been evaluated. And then I'm going to evaluate this 8 times 8 minus 8 squared over, oops, I forgot to close my parentheses there, 8 squared over 2. That's the first one. And then I'm going to subtract 8 times 0 minus 0 squared over 2. Close those final brackets. Now some of these, obviously, this whole term here goes to 0, so I can ignore that. This term inside here goes to 0, so I can ignore that. I'm just going to rewrite it one more time. 32 thirds times 8 to the 3 halves minus 0 plus 8 times 8, I'll write that as 64, minus 8 squared over 2. Well, 8 squared is 64. Half of that is 32. Term by term addition here, I'm going to get 32 for those. So I have pi times 32 thirds. Now the way I do these is that 8 to the 3 halves is the 1/2 of the square root of 8 and then cubed. So this is equivalent to, well, that doesn't really help, does it? 8 doesn't have a perfect square root. But the square root of 8 cubed. The square root of 8 is 4 times 2, so this is going to be 2 root 2. 2 cubed is 8. Root 2 cubed is 2 root 2. So this is 16 root 2. So that's really all I usually do with those is 16 root 2. It's just simplifying that, plus 32. And at this point, I would say, depending on the situation, maybe even all the way back up here somewhere, you could probably stick this in your calculator. Maybe that's a little too far back. Maybe we could put it in our calculator about here. But I really like exact values, so I'm going to keep going here. This is pi, let's see, 32 times 16, 19, and 32. So 2, 11, that's 5, 12. So this is 16 times 32 there. Is 512. So I have 512 root 2 over 3 plus 32. And since the first term is over 3, so I'm going to write this as 32 times 3 over 3, so times 1, so I can find myself a common denominator. That gives me 512 root 2 plus 96 all over 3. And then I could write that also as 512 root 2 plus 96 all times pi all over 3. And that's the exact value of this. Let me go grab my calculator and see what it works out to as an approximation. Okay, I get here 858.7829 or 7830 if I round to 4 decimal places. And that is not the right answer. But because I had the recording turned off there for a minute, I went ahead and went back to see if I could figure out where the problem was. And it was a really minor algebra error. Sometimes when I make these videos, I actually erase the first screen. This time I didn't, and I'm really glad I didn't because I can go back to my first screen. That should be a minus, and that's a plus, and a minus, and a plus. And I'm just going to carry on doing this until we figure out that's a minus and a plus, which makes this negative 32. That's minus 32. That was just finding a common denominator. So now I'm going to plug this into the calculator again. Okay, I'm back, and this time what I get here is, actually I don't need to do all of that. This just turns out to be a minus. And my new approximation is 657.71, nope, 7211. And that is the correct answer. So I hope that was helpful. You got to see me make a mistake and go back and figure out how to fix it. Of course, I did the bulk of that part off screen or off the recording. Took me about a minute to find the place, going back through my work to find the place where I had made the error and then be able to fix it. So I hope that's helpful. As I said at the beginning,